right, so coterminal angles, radian and degree conversion, and then this thing we're going to talk about today, related to circles and so forth. And that's probably what we'll spend a lot of our time working on. But we've got to get comfortable with this idea of radian and degree to help us in those problems as well. So again, there's an equivalence here, right? They're different type of units, but it's kind of like, in some ways, it's like saying, okay, 2.54 centimeters is 1 inch. I mean, so 2.54 is equal to 1? No, not really. 2.54 and 1 are not equal. But when you add the units, then they are, right? So 2.54 centimeters, I think I have that right. I don't know, something like that, whatever. Okay. Is that right? Okay. So 2.54 centimeters equals 1 inch. So when you put those units on them, then they're equivalent. Okay, you take the units off, and then, you know, it's not, obviously. Well, the same thing is true here. 3.14 radians, well, that's abbreviated, right, or that's rounded, 3.1459 pi radians is equal to 180 degrees, okay? And so we talk about pi is equal to 180, or 2 pi is equal to 360. Again, we mean 360 degrees. So a lot of times we substitute a 180 in for pi, right? We substitute a 180 in for pi, but keep in mind that pi is also 3.14, right, as a number. And so when we talk about pi radians, that's 3.14 radians, but pi radians is 180 degrees, okay? So understand the difference. And of course, my hope is every time you hear radian, you probably end up thinking of two things. You'll think of pi, it's something in terms of pi, because most times radians we do put in terms of pi. But I also hope you'll think radian and radius, and you'll think about what we did with the string. And you'll think, okay, well, that's in a circle. If I take the radius and I go around the circle, 1 radius, 2 radius, 3 radius, 4, 5, and 6, that's radian measure as well, okay? And so when we put an angle into there, like, let's say we just put in whatever, something like that, that we could look at that and we can think of that as a rotation, which would be more like degrees, or we can think of it as this, the length of that opening, and it's actually not just the length of that opening, but it's the length of that opening divided by the radius. Now, what you will find out, what we will do next week, is we will talk about something called the unit circle. And all the unit circle is this circle on the XY axis with a radius 1. Since it doesn't really matter how big the circle is, remember when we were doing that, when we were looking, some of you had a smaller circle, some of you had a bigger circle, and this is, in any circle you pick, 1 radian is going to go about that far, then 2 radian, 3 radian, it's all going to be the same no matter how big the circle is. So why not pick a circle that's easy to work with? So let's pick one where the radius is 1. Well, if the radius is 1, then the angle truly is just the arc length. Okay, and so if the radius is 1 on this, then it actually is 6.28 units around the circle, right? Because again, what is circumference? 2 pi r. The radius is 1, the circumference is 2 pi. Okay, so the angle, this angle on the unit circle, this angle is truly this length right here. Okay, now in a generic circle, the radian, this angle is this length divided by the radius. Okay, all right, so that again is just an idea of radian measure. So some important fractions to know would be these in the red, but also some important decimals to know are these in the blue. 1.57 is half of pi. 3.14, of course. This is one you probably haven't seen before, but that's 3 pi over 2. That's 4.71. Okay, those are some numbers that should jump out at you from here on out as decimals, as kind of important decimals. Okay. All right, so that's what we had. So let's look at a few of the homework questions. I just picked out a couple. So we're converting back and forth from one to the other. Now, yesterday, I think the important thing to remember is I hesitate. I don't want you to memorize things, really here. There is some things I'm going to tell you it's important to memorize. But here I would hope that it's more about if you're going from degrees to radians, that's the time we want to multiply by pi over 180. Now, why is that? Well, because degrees are in the bottom. And so if you're going from degrees to radians, you want degrees to disappear. You want degrees to go away. So by putting degrees in the bottom, they will cancel. And I guess that's just what has worked for me over time to remember this. Okay, if I'm going from degrees to radians, I want degrees to disappear. So I'm going to multiply by pi over 180. Now likewise, if I'm going from radians to degrees, now it kind of depends. Now it kind of depends, because when I go from degrees to radians, I'm always going to be given degrees as just a number, 120 degrees. Now it might be degree, minutes, seconds, but then I'll just use my calculator to get it into a decimal. But I'm just going to have a number, 120, 60, negative 470, whatever. It's just going to be a number. But radians could be given to me in two different ways. See, radians could be given to me as the red, where I have a pi in it, or radians could be given to me as the blue, where it's just a number. You see what I mean? So so radians to degrees is a little different. So if I'm given radians like this, then what am I going to do to convert to degrees? I would not times by 180 over pi, but if you want to, that's fine. For some of you, understand, that's going to make sense. You're just going to remember, you're going to times by 180 over pi every time, and you're just going to do that. And I think that's wonderful. That's great. Now, I haven't really done it. It makes sense to me, but that would work. And you might say, well, that's stupid. Why wouldn't that make sense to you? You just told us that you want degrees in the bottom, so they'll cancel. So if you're going radians to degrees, you want the radians to cancel, right? So I think I'll put the pi in the bottom, because then it'll cancel. So I get it. That would be a great way to remember it. I don't know why that's never worked for me. When I see this, I do what? What did I tell you yesterday? Yeah, I just put a 180 in for pi. That has always just made more sense to me. But I don't care. What Charlie said is exactly right. You just times by 180 over pi, because that's what we're going to do in my other example. Okay? So I just do this. Okay? And so I get 120 degrees. But what if I'm giving it, as 2.68 radians? Right? Then what? Then all of a sudden I can't do this thing, right? So that's where I would say, well, you'll go ahead and times by, so you'll take 2.68 times 180 over pi. And so it's radians down here cancels the radians here. Okay, and you're left with degrees, and so that's what you do it. Now, also, Noah, you kind of said something different, right? You said, why not take 2.68, which is so many radians out of, what did you say, 2 pi? Did you say to do that? Yeah. You just said you would take 2.68 and divide it by 2 pi. That's a fraction of the circle, and then times that by 360. Now, in a sense, that's the same as doing that, right? It's the same as doing that. So I don't care. All of those are okay. They all, whatever makes sense to you is probably what, you should do. Okay, but the bottom line is going radians to degrees, you want the radians to cancel out and be left with degrees. Going from degrees to radians, you want the degrees to cancel out and be left with radians. Okay, so that's kind of the gist of what we were talking about yesterday. So here I got 60 degrees, so I'm going to multiply by pi over 180. I'm going to reduce negative pi thirds. Now, it did say in the directions to write it in terms of pi. Now, I went ahead and just put the decimal over here, which would just be 3.14 divided by that. Now, here's another thing I think I want us to do. I haven't decided if my thinking right now is I'd rather you use the pi button, so you get all the decimals of pi, not all of them, but a lot of the decimals of pi to make our answer more accurate, rather than type in 3.14. How many people have been using the pi button on their calculator? Okay, a lot of you have. All right. I think I would rather us do that. Now, I may write down 3.14, or I may say 3.14 divided by 3, but what I really am meaning for you to type in is the pi button, so you get a bunch of decimals. Now, at least put in 4 or 5. going to type it in. Okay, 3.14159, isn't that 5 decimal places of pi? 3.14159, type that in. At least that way you'll get a pretty good answer out to 2 or 3 decimal places. Okay, and so anyway, back to this, negative 60 degrees would be down here. I just kind of wanted to check this out. I kind of wanted to check out this decimal and just think about this. If I go this way, remember, this would be negative 1.57 here. If I'm going this way, negative 3.14, negative 4.71, negative 1.0 should be right in here somewhere. So negative 60 kind of makes sense. Okay, I just want you to really start getting a handle on the quadrant that these things are in. Okay, here's this one. Now here's what I did. See, if I did 3.14, I got this. If I did the pi button, I got this. So it makes a difference out to the third decimal place. Now I think if I would have typed in 3.14159, then I think I probably still would have been okay. All right, but anyway, there's our answer. So this is 216 degrees, which makes sense to be over here. 3.77. Sure enough, this is 3.14, and then a little farther. Okay. All right. Here's a kind of a strange one. We don't usually combine decimals with pi. Most of the time, it's whole numbers and fractions. But we need to be able to handle it, right? So if I'm going to degrees on this, I'm probably just plugging in 1/8 for the pi. Okay, but I was curious if to make sure everybody understands the rotation of this. Negative 4.2 pi would mean, how far did I just go? How far did I just go? Now let's talk radians now. I just went negative 2 pi, right? Because I'm going backwards. And now I just went negative 4 pi. So now I need to go just a little more, right? It's 4.2 pi. So that's twice around in the negative direction and then a little more. So it should put me in the fourth quadrant. Negative 756, well, twice around would be negative 720, right? And then 36 more. So it makes sense that would be there. Okay? And here's number 79. So again, I just picked a couple out. So 79, negative 2. Again, there's no degree symbol on it. If there's no degree symbol on it, it's radian. Okay? It's radian. So you can have negative 2 degrees, but that's not what this is. So negative 2, again, think of our string. Here's 1. Here's 2. Right? 2 pieces of string. 2 radians should be about that far. Okay? And so, since that's radians, I want the pi's, I want the radians to cancel. And this would be radians down here. This is degrees. So this is radians. So when I multiply, it's like those cancel. I'm left with degrees. I got this right here, which makes sense. Negative 114 would be about that far. And then this was what I just wrote down what Noah, you had said the other day. Where it's the same thing. Okay? All right. Any other questions on any of those? Okay? All right. So if we can get a good handle on this radian stuff, then we'll be good. All right. Let's go ahead and do those 5 just quick little warm-up problems here. Now notice there's a double arrow there, so radian degrees means you could be going radians to degrees, you could be going degrees to radians. Okay, that's. number 3, put that in decimal degrees and in degree minutes seconds. Just for the heck of it. Okay, what are you getting for number 1? Okay, in terms of pi. 7 pi over 18. Okay. Now, I'll try to be clear on the directions. Typically, when we convert to radians, we'll leave it in terms of pi. Unless it's like a really strange decimal, like if I gave you, 70.163 degrees, and said radians, and maybe it's a decimal. Or maybe give both if you're unsure. Give 7 pi over 18 and give the decimal version of it, I think would be okay. And I may ask you that on the quiz too, just give both, to convert this into radians, both in terms of pi and as a decimal. Okay, so I might do that. Number 2, 108 degrees. And number 3, 229.18 degrees. What about degree minutes seconds? I had 229 degrees, 10 minutes, 59 seconds is what I had. Now, I used the pi button, so I did 4 times 180 divided by pi button, it equals, and I had 229.183 something, something, something. And then I went to the degree minute second conversion on the calculator, and it said 229 degrees, 10 minutes, 59 seconds. Okay. So again, that's one where using the pi button might make a little bit of difference. So if you had something different than that, talk to me later here when we have some work time. I can, if you're having trouble getting that. But okay. So that's the only thing we'll do with degree minutes seconds is just type it into the calculator and convert back and forth. Type it in each way. Okay, now it's 4 and 5. So this is a little bit new now, but this is a really critical thing with working with radians is how are you going to add 3 pi 4s plus 2 pi? Do what? Like, what do you mean? No, because we don't want to simplify. Doesn't mean convert. We want to keep this in terms of pi. Okay, so sorry about that. I wasn't real clear on those directions. This is the first time we've seen this. Simplify means add those together, but keep it in terms of pi. We need a common denominator. Common denominator. So this is going to get, you're going to hear me talk about these fractions in a certain way. So when I hear, a couple of things. Let's talk about a couple things here. When I hear 3 pi over 4, here's how I hear that. 3 pi over 4s, right? So I know, and you'll get really good at this, pi over 4 is 45 degrees, right? Pi over 4 is 45 degrees. Again, you're good. That's just going to become automatic. So when I hear 3 pi over 4, I think, okay, there's 1 pi over 4, 2 pi over 4, which would be pi over 2, right? That's 90. And then 3 pi over 4, right? If I hear 7 pi over 4, I think of counting. 1 pi over 4, 2 pi over 4, 3 pi, around to 7 pi over 4, okay? I think that's helpful in these problems, okay? That's one. Second thing is getting common denominators is critical, okay? So we're going to change 2 pi to 8 pi over 4. Then you got 3 pi over 4 plus 8 pi over 4, and what is that? 11 pi over 4. Okay, so 3 pi over 4 plus 8 pi over 4 is 11 pi over 4, and that's how we want to do it. And we want it as improper. We don't want to say, we don't want to say 2 3/4 pi. We don't want to say that. We want to say 11 pi over 4 because, again, it's kind of like that counting thing. 11 pi over 4 means pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, and so forth, right? That's what 11 pi over 4 should mean to us. I think that's helpful. So on number 5, we're going to change 2 pi to what? 12 pi over 6. So this is 1 pi over 6, take away 12 pi over 6. So the answer is negative 11 pi over 6. So radians is going to force us to get really good with common denominators and with improper fractions, because that's how we're going to write. Okay, we do not want to write that as 1, negative 1, and 5/6 pi. Okay, that's not how we're going to write. Okay, now the nice thing is most of the time we're not dealing with fractions like 7 pi over 18 or something like that. Our most common fractions, and I think, let me see if I have that guy up here. No, I don't. Okay. Let me pull up yesterday's. Let me pull up yesterday's real quick. There we go. Okay, so you notice these are, again, what we said are going to be kind of our main angles that we're going to work with. These are the ones we're going to do by memory, okay, when it gets down to it. And look at your fractions. They're out pi over 6, pi over 4, pi over 3, and, of course, pi over 2. And those are going to be the denominators we will work with most of the time. So thirds and fourths and sixths, and that gets us all the way around the thing. Right? I mean, for example, pi over 6. When I hear that, I think 1 pi over 6. So that's 30 degrees. 1 pi over 6. Well, another pi over 6, that's 2 pi over 6. Well, what's that reduced to? Pi thirds, right? 2 pi over 6 would be pi thirds. 3 pi over 6 is another 30 degrees. 3 pi over 6, oh, that's pi halves. 4 pi over 6, that's 2 pi thirds. 5 pi over 6. And so what we will be doing a lot is when I think of pi, I'm going to think of that as 6 pi over 6. I might think of that as 4 pi over 4. I might think of that as 3 pi over 3, depending on which angles I'm working with, right? And so pi over 3. Here's 1 pi over 3. Here's 2 pi over 3. Here would be 3 pi over 3. Here's 4 pi over 3. Here's 5 pi over 3. And then, of course, this would be 6 pi over 3, which is 2 pi. Right? So 2 pi, a lot of times we'll think of as 6 pi over 3. We'll think of it as 8 pi over 4. We'll think of it as 12 pi over 6, like you just got done doing in that problem. Okay? So getting these common denominators to work with is something that's really helpful when we're working with our radian measures around this circle. Okay? All right. So, moving on. So, back to coterminal. The first thing we did in this chapter 4, we were doing those coterminal. What are you going to do if I give you, and think about the warm-up we just did, if I give you an angle like 7 pi 6, and I want you to give me a positive angle that's coterminal to that, what are you going to do? You're going to add or subtract what? No. Your mind? 2 pi. 360s in what? That's degrees. That's degrees, right? Earlier, we said add or subtract 360. If we're in radians, we're going to add or subtract 2 pi. So if I want a coterm, this is part of your homework, I think tonight you're going to do this. So if I want a positive coterminal, I'm going to add 2 pi. So, what would that do? What would that equal?
19 pi over 6.
Very good. 19 pi over 6, right? Because in your head, probably, you're just going to convert, you're just going to change 2 pi into 12 pi over 6. You're just going to, mentally or write it down, whatever, but you're just going to change 2 pi into 12 pi over 6. And so 7 pi over 6 plus 12 pi over 6 is going to be 19 pi over 6. Now I want a negative one, okay? 7 pi over 6 minus 12 pi over 6 is negative 5 pi over 6. Okay? Negative 5 pi. So there's a positive coterminal and a negative coterminal. Remember, 2 pi and 360 degrees are interchangeable. But one's in degrees and one's in radians. So if the problem's in radians, we want to stay in radians. One of the things you'll notice today, so if we're doing coterminal, if the problem starts in radians, you leave it in radians. If it starts in degrees, you leave it in degrees. Okay? So let's look at 7 pi 6 on this picture. Where was 7 pi 6? 7 pi 6 was right here. So if I go around to 7 pi 6, right, the negative version of that, wouldn't that be negative 5 pi 6? Right? Wouldn't that be negative 5 pi 6? Let's count them out. There'd be 1 pi 6 going in the negative direction. 1 pi 6, 2 pi 6, 3 pi 6. I'm going in 30-degree increments. 1 pi 6, 2 pi 6, 3 pi 6, 4 pi 6, 5 pi 6. Negative 5 pi 6. Right? Okay. So, we want to get real used to those things. We'll keep working on that. All right. So, dang it. What was I thinking? All right. But you didn't see that. Like an idiot, I showed it to you twice. Come on. That's why I make little notes to myself when I hear that shit. Okay. Aha! Whoa! Sketch that. First of all, just write which quadrant's it in. Pretend you didn't see it if you did already. See if you can just mentally in your head think about which quadrant that's in without even sketching it, and then sketch it. Okay, see if you can just look at that angle, tell what quadrant it's going to be in, and then sketch it. Now, I'm trying to wean you off of degrees a little bit, right? Now, I get it where you might take, and I think I probably did this when I was first learning too, and now I've worked with it so long I don't need to, but I could see some of you, I mean, admit it, how many people would put a 180 in for pi and see what the degrees were, right? Okay, and that's not awful, okay, but it would be nice if we could get away from that, okay, if you could get away from that. Now again, it's okay, that's the equivalent, but if we have to do that all the time, that probably takes more time than we need to. So, let me talk about what I think the thought process would be. If I'm looking at negative 5 pi 6, my thought process goes right to, because I want to know the quadrants. So my thought process goes right to 0, pi halves, pi, right? Those numbers. The very first picture we had up here today. See, I want to go to these numbers. That's what I'm thinking of right here. Okay? So when I see 5 pi 6, right away, I'm thinking of 6 pi 6 right over here. 6 pi 6 right over here. So now, when I get back to this problem, okay, now I'm thinking, all right, 6, so if I go negative direction, 6 pi 6 would take me over to the 180 line, but I'm short of that. I don't have 6 pi 6. I only have 5 pi 6. So I'm short of that. So what quadrant? 3. So it's got to be in 3. Okay? So that's my thought process for that one. Okay, when I see negative 3.9, now what numbers come to mind? Well, now these glue numbers come to mind. Okay? Or the string comes to mind. Okay, so now it's like, okay, I need negative 3.9 radians or radius, so I got to go around 1, 2, 3 was just short, 4 is going to go up into quadrant what? Quadrant 2. Now again, what comes to mind for me is negative 3.14. If I go negative, I'm going to come around here to 3.14. If I keep going, what's the one up here? Right? If I come around to here and then up to here, that's 4.71. Well, I'm short of that, negative 3.9. So I'm past negative 3.14 as I go around, but I'm short of 4.71. So it's going to be up here in quadrant 2 somewhere. Okay? So those, again, I would like you to start to get into that mindset as opposed to going back and forth the degrees all the time. Okay? All right, but we're just starting it, so I get it. You know, that you're comfortable with degrees, so you want to go to that. All right, how about this one? Do the same thing for this one. Which quadrant, and then sketch it. If you can, try to do it without thinking of degrees. Try to do it with just fractions. What quadrant? Quadrant 1. What fraction of this might come to mind? Now, first, when I see thirds, I might think of 3 pi thirds, right? But then I quickly say, well, geez, there's more than that. There's not even 3 pi thirds. There's 6 pi thirds. That's 2 pi. There's even more than that. So as I'm thinking of that, I'm saying, okay, 6 pi thirds, that's 2 pi. That's all the way around. 6 pi thirds, again, I'm thinking of counting. How many pi thirds do I have? I have 6 of them. 6 pi thirds, that's 2 pi. Takes me all the way there, but then I got one more. I got one more to get to 7. Well, 1 pi third is going to be right in there. Okay, 1 pi third more than 6 pi thirds, right? Again, I think that's a good way to think about it. Yeah, you can go to degrees and get the same Same idea, okay? But you're thinking of 2 pi being 6 pi thirds. All right, what else do I have? Okay, give me one positive and one negative coterminal for each of those. Sketch it. Give me one positive and one negative coterminal. Sketch it and give me one positive, one negative. All right, so as you're finished, some of you are getting done. As you're finishing up here, I'll just talk quickly. So again, I'm looking at this as fractions. I mean, think about this. You got to do one positive, one negative. You change it to degrees. Then you got to add or subtract 360 to get two of them, one of each. And then you got to change it back to radians. Because remember, the rule is if the angle that you're given is in radians, the answer you give has to be in radians. Okay? And if you're giving it in degrees, then you give your answer in degrees. So you would have to convert and it converts back. Again, you can do it. I'm not going to count it wrong, but that's probably something you want to try to get away from doing, okay, and learn this. So when I see 5 pi thirds, I'm going to think of 6 pi thirds, right? And when I see 2 pi over 15, I'm going to think of what? To add or subtract. Huh? 30 pi over 15, right? What's 2 pi? 2 pi is 30 pi over 15. That would be 2 pi. Okay, so I'm going to add 30 pi over 15 and subtract. Let's do the top one here first. Okay, so I'm going to add 6 pi thirds and I'm going to take away 6 pi thirds. Okay, just like we added 360 and subtracted 360, we can add 2 pi, we can take away 2 pi. That's one full rotation. All right, so 5 pi thirds and 6 pi thirds is 11 pi thirds. 5 pi thirds take away 6 pi thirds would be negative 1 pi third. Okay, and then likewise down here, we said we would add 30 pi over 15 and we would take away 30 pi over 15. So that gives you 28 pi over 15, and that gives you negative 32 pi over 15, right? I mean, it's just like adding like terms, just like adding x's together, adding pi's together, same thing. 2 pi plus 3 pi is 5 pi, right? I mean, it's very much the same idea. Okay, so we're going to have just about enough time to watch a little video here that's going to take us into the next new thing we're going to talk about. And we're going to talk about it a lot after lunch. However, your homework is pretty much going to be what we were just working on. Coterminal, radians, getting comfortable with that one more day. But we're going to jump into this next thing we're going to talk about, which can be confusing for people. It shouldn't be, but it is, and it takes you a little while, but after a couple days, by Friday, hopefully we're ready to go. Okay, so let's go ahead and now this, person in the video is not probably as exciting as listening to me, but that's, who is, right? So
in this video, we're going to be discussing the concepts of linear and angular velocity as they relate to points traveling on circles. In this diagram, we have two circles, the red circle and the green circle, and we have point A on the red and point B on the green. What we're going to be doing is animating these points so that they're traveling on their circles in a counterclockwise direction at the same linear velocity. Now, when we say linear velocity, we're talking about speed as we know it, which could be measured in inches per second, feet per minute, miles per hour. Linear velocity is what we're used to thinking of when we talk about a rate of speed.
Okay, now that was actually really important what she just said there. You can tell by the way she really changed her voice and made it really sound important. So the linear velocity, okay, means speed in a line, in a distance, okay? Angular velocity means the speed more as an angle. So the units are really, really key here, okay? So when we talk about linear velocity, what she said is that's like feet per second, miles per hour, that kind of thing, okay? The top of the fraction is going to be a distance, and the bottom of the fraction is going to be the time, okay? All right. So notice both points are covering the same.
Now, the reason we know these are traveling at the same rate of speed is that the motion controller at the bottom of the screen is showing us that the speed is 1 for both of these. And we're not sure what the unit of measurement is, but it's the same for both. At this point also, since we've stopped this, we can talk a little bit quickly about angular velocity. Angular velocity means if this point has traveled through a certain number of degrees on a circle in a given amount of time, we can talk about angular velocity. Since point A has traveled approximately through 365 degrees in the same amount of time that point B traveled through approximately 365 degrees, that they seem to also have the same angular velocity. Angular velocity is measured in degrees per second, degrees per minute, radians per hour, that type of unit of measurement.
Okay, so there's the key difference. Linear velocity is going to be a distance divided by time, inches per second, miles per hour, feet per minute. Angular velocity is going to be an angle divided by time. So it's either going to be degrees per time unit, degrees per second, or it will be radians per second, or radians per minute, whatever. Two equal circles, those 2 points will have the same linear and the same angular velocity. They're traveling the same distance per unit time, but they're also traveling the same angle per unit time.
Degrees, which measures angles per unit of time. Now what I'm going to do here is change the size of the green circle fairly drastically, and then we're going to animate these points again. Now again, the linear velocity is going to be the same for both.
And that's because, and the reason the linear velocity is going to be the same is she has set it that way here in this control. So she has set that this point A and this point B are each going to cover the same inches per second as they go around, okay?
But what we can see now is that point B seems to be going through more degrees per second than point A. In fact, we can say that point B is going to complete more revolutions, complete revolutions around its circle than point A will.
Now, if you really focus on point A and point B and imagine those two different people running, does one of them look faster than the other? Now, my sense is if you just watch that without me saying anything, you would have said B's going faster. But if you watch them real carefully,
in the same amount of time, the angular velocities are very different now for these.
Do you think they're going different speeds? They're not, right? And that's what I just said. Their speed is set right here, so they're both going the same distance per time. Okay, we'll come back to that. Oh, thank you.
Going through more degrees per second than point A. In fact, we can say that point B is going to complete more revolutions, complete revolutions around its circle than point A will in the same amount of time. The angular velocities are very different now for these two circles, whereas the linear velocity, as we can see, is still the same for both. And briefly, we can especially see it in that last little bit of movement. Angle A seems to have traveled through approximately 65-70 degrees perhaps, whereas angle B has traveled to about 120 degrees in the same amount of time. That means that their angular velocity is not the same, whereas their linear velocity, as we've seen on the bottom of the screen, has remained the same for both.
Okay, so let's say that was 1 second. This point has went 65 degrees per second. This one looks like it's went about 120 degrees per second. They have two different angular velocities. Likewise, this one has went through this distance, however many inches that is.
In this diagram, we have the two circles. We can especially see it in that last little bit of movement.
Okay. This one has went through this distance in, let's say, a second. This one has went through this distance in a second. What does it look like, those distances? Don't they look like they could be roughly equal? This one has went from here around to here. That looks like that might be about the same number of inches as this one has traveled. Okay? That's a key component.
Angle A seems to have traveled through approximately, B has traveled to about 120 degrees in the same amount of time. That means that their angular velocity is not the same, whereas their linear velocity, as we've seen on the bottom of the screen, has remained the same for both points. In this diagram, we have the two circles, the red circle and the green circle. The green circle is markedly smaller, and what we're going to be looking at here is 2 points on two different sized circles, which are traveling at basically roughly the same angular velocity.
Okay, so now we're flipping it. Now they're going to go through the same angle in the same amount of time. So they're both going to go 90 degrees, let's say, in 1 second. Okay, tell me what you think about this point compared to this point if they're both going to go 90 degrees each second. Which one? This one's got to go faster. I mean, as far as, think of this as a track, right? This one's running around a big track. This one's running around a little track. And this one needs to get 1/4 of the way in the same time this one gets 1/4 of the way. He's got to run faster because he's going a greater distance. So his angular velocity is the same, but the linear velocity now is different.
Again, if I pause this at some point close to roughly the same angle measurement or degree measurement that point has passed through for both. And again, a little bit past 90 degrees for both of these. One thing I would like to point out is that this is just a demonstration video. There are formulas that we're going to be dealing with in terms of linear and angular velocity and sine.
And then I'm going to stop it here. And then she goes down here to show that the speed of this one is double the speed of this one. And look at the radius. The radius is double, so it's not a coincidence. But there is that connection. But anyway, we want to hopefully get from this. The pictures are what I was really interested in. I tried to draw these myself in the program, and I'm not smart. So anyway, I just tried to do it last night. I didn't have enough time. So I thought, okay, I'll show this video because it kind of shows the same thing. So angular velocity versus linear velocity, okay? And again, we're talking, a lot of these problems we're going to talk about is going to be motion in a circle, right? Motion in a circle is what we're looking at. Okay, so let's go ahead and pick up from there. And now let's get into some of these formulas we're talking about. But again, they're not really formulas so much as they are just dividing. I mean, let's think about it. I mean, so if you want to look at this, I've got two circles here. Again, I've got a small and a big, just to kind of show what she was talking about. And so linear velocity is, and we're going to use S because we've been using S as our arc length. Since we're doing motion in a circle, our distance is going to be an arc. So our distance is going to be measured like so. Okay, so distance, we'll use S as our variable.
We're going to the back of this paper for something else.
Where you have the circles?
Yeah.
No. I don't care.
Yeah, you keep it.
All right. So S is the distance divided by a time. That's how you do a rate. Distance divided by time. So if it's inches per second, you want to take inches divided by seconds. Feet per minute, you want to take feet divided by minutes, right? The fraction bar here is a divide. So S divided by T. That's linear velocity. We use V because that's our normal velocity. When we think of velocity, we usually think miles per hour. We usually think feet per second, something like that. The new one for us is this idea of angular velocity, right? That's not something we've talked a lot about that you've heard before. Now, the book uses the Greek letter omega, and the lowercase for omega is kind of a W, okay? So you might see that. I won't use it a whole lot, to be honest with you, but that's your angular velocity, okay? So if you see that, that's what they're talking about. But that's just going to be theta divided by T. It's an angle divided by time. It's degrees per second. It's radians per second or minute or hours or whatever. So angular velocity at the top is always going to be either degrees or radians. And the bottom is always going to be a time. To me, those are the only two formulas you really need. Now, I'm going to give you some others here. And so I think common sense should apply for most of these, but I'm going to give them to you because you might be more comfortable using those. Okay? So again, we're talking about motion in a circle. Right now, these two dots, if they were moving, would have the same which velocity right now? The blue and the red, if they had both started at 0 and went for a second, they'd have the same what? Angular velocity. But the red dot has traveled farther. The red dot has traveled farther than the blue dot as a distance. So it would be going faster. It would have a higher linear velocity than the blue dot. But they would have the same angular velocity because they both went about 45 degrees in whatever time. Okay? All right. So here's some other formulas. Now, this formula over here on the left, theta equals S over R, is a formula we already talked about with radians. Now, our linear and angular velocity discussions are most of the time going to be in radians. We may get a few problems that have degrees in it, but most of these are going to be in radians. Now, here's an advantage to using radians, because this formula down here only works if theta is in radians. Right? This formula down here only works if theta is in radians. Same with this one up here. Matter of fact, all of these formulas, well, except for this very bottom one, only work if theta is in radians. Okay, now this bottom one is just angular velocity, and that's just theta divided by t. So if something goes 240 degrees in 2 seconds, What's its angular velocity? Let me say it again. If a particle goes 240 degrees in 2 seconds, what's its angular velocity? 120 degrees per second. You just divide it. That's that easy, right? If something goes 240 degrees in 2 seconds, its angular velocity is 120 degrees per second. So this formula could be in degrees. But the rest of these only work if theta is in radians. Okay? Has to be in radians, okay? Because they come from this. They come from this, and this is radians. This is the definition of a radian angle right here, is the arc length divided by the radius. We talked about that earlier today. Okay, so if I multiply the r over to the other side, I get arc length S equals r theta. This can be a pretty handy little formula right here. Arc length equals radius times theta. Now remember, we said if we use the unit circle, which just has a radius 1, if the radius is 1, then the arc length is the angle, right? That's what we were saying earlier. The arc length is the angle, okay, as we went around that circle. But if the radius isn't 1, then we have to have that in there. So that could be a handy little formula right there, S equals r theta. So you'll hear me say that quite a bit, S equals r theta. Okay, but again, that has to be in radians. We could make one that was in degrees, but it would be messier than this. That's one of the advantages, again, to use radians. Okay, linear velocity. So let's go over here. Linear velocity. Now I put this in red because that's what we have on the other page. Linear velocity is just a distance divided by a time. S, remember, is just arc length. S is just that distance around the arc. Okay? So that's just distance divided by time. But we just got done saying that S is the same as r theta. Okay? So we can make a substitution. If S is equal to r theta, put an r theta up there. Okay? And that's fine. But now I notice that, wait a minute, if V is equal to r theta over t, another way to write that would be r times theta over t. Would you agree with that? Do you agree with those are equal? And what did we say theta over t is? What's theta over t? Angular velocity, right? So this is just r times the angular velocity. So this can be a nice little formula here that relates the two. This relates linear and angular velocity. So the velocity, the linear velocity, is simply the radius times the angular velocity. Now that makes sense because what did we say? We said if two things have the same angular velocity, the one on the bigger radius is going faster. So the longer the radius, the faster it has to go to keep up, right? Now imagine you ever play this when you're a kid, when you get a whole line of people and the person on one end of the line and everybody starts running around, you whip the line around, right? You ever done that? We should do that. Maybe we should. Let's go outside. No. Okay. But, yeah, you know what I'm saying? No, you hang out, you get a long line, and you start whipping around. What happens to the person clear at the end? Yeah, they go flying, right? Because they all have the same angular velocity. If you guys all turn around in 1 second, if you do one full revolution in 1 second, you all have 2 pi radians per second, right? Everybody's going around 2 pi in 1 second. That person on the end's got to flop. And, the people on the inside are just kind of doing this. They're barely moving. And that person on the outside's got to fly to go around because they got a lot more room to cover. Okay, that's angular and linear velocity right there. Okay? All right. So this little formula kind of connects the two. So maybe that comes in handy. But to be honest, I'm not sure you ever really need it. I think you can typically just think your way through it with multiply and divide because that's what all of these do. Okay, we'll see as we get into them. Your homework tonight's not going to have any of those yet. We'll work on some more tomorrow. Okay, so let's do this little activity here in your notes. Because so I just got in saying that I don't really want you to memorize the formulas, but to think them through. And the key to thinking them through, what my experience has been, is just units. If they want you to get your answer in miles per hour, then what I think is almost the easiest way to do these problems, instead of trying to memorize formulas, is to take what they give you and make the units come out miles per hour. And it's almost foolproof. Now, in science class, they do this. I don't know, anybody been in chemistry already this year? You're doing it now. Okay, and so in chemistry class, isn't it chemistry class where you do some of this where you go like this, you make units cancel and stuff like that? Okay, that's what, I think that just works really well. So let's imagine we had a problem. This doesn't have anything to do with angular and linear velocity. This is just talking about how to make units come out. Okay, so let's say you've got a car, you're going to drive 60 miles an hour, gas is $3 a gallon, and your car gets 20 miles per gallon. How much is that costing you per mile? So, you sat there and go, geez, okay, would I divide? Am I going to do 3 divided by 60? Am I going to do 20? What am I going to do, right? It's not that hard. How much per mile? What do I want my final answer to be? Dollars over miles. That's what I want. So which of these 3 numbers do I need? Do I need all 3? Do I just need 2? I really think, do I need gallons to be involved at all? Here I've got, or do I? Do I need hours to be involved at all? I need dollars and miles. Which one has dollars? Well, that one, so I definitely need that one. It's the only one that has dollars. Okay? But that's got gallons in it. I don't want gallons, so I need something that'll get rid of gallons. So I better have another one with gallons in it, right? Now look what that's got. That's got dollars, that's got miles, and they both have gallons. I'll bet I can get the gallons to cancel. You see what I'm saying? So this is how I'm going to set this up. So I'm going to go 3. Now I want dollars on top when I'm done, right? So I'm going to put $3 on top and 1 gallon on the bottom, right? Isn't that $3 per gallon right there? Okay, now what do I want to cancel? I want gallons to cancel. So I'm going to need gallons up here, and what do I want to end up with down here? And you can't always make this happen in one step, but this time it looks like I'm going to, because now gallons are going to cancel gallons. But what am I going to put where here? It's 20 miles per gallon. So where's the 20 going? 20's got to go on the bottom. It's 20 miles for 1 gallon. And there you go. It's 3 divided by 20. Now maybe some of you could have just looked at this and knew how much per mile, and you were just going to take 3 divided by 20. Maybe you knew that. Okay? But I'm not that smart. So what does it end up being? What is that, 0.15? So what did we just find out? It's cost us 15 cents per mile. Okay, let's move to the next one. How much per hour? How much is it costing me to drive that car every hour? It's costing me 15 cents per mile, but let's pretend I hadn't even done that. So let's start from scratch again. How much per hour? Okay, well now I need dollars, so I need this one. I need hours, so I need this one. But I got to get rid of gallons, so I'm probably going to need all 3. Okay, so where do I start? Well, I always start by what's going to be on top. How much per hour? What do I want on top? Money, dollars. I need dollars on top, right? So I'm going to start with the $3. So $3, 1 gallon. That's dollars per gallon. Okay, now what do I want to end up with? I want to end up with dollars per hour, right? So what do I need to cancel? I need gallons to get out of it. So what am I going to do? I'm going to do the same thing I just had here. Miles. Oops, I need gallons up here. I need gallons. I need miles. So what was it? 20 was here, right? 20 miles, 1 gallon. Okay, gallons are going to cancel. Now I got dollars per mile. Well, I need miles to get out of it, right? So I'm going to put miles up here so they'll cancel, and I need hours down here. What do I put here? Miles per hour. Oh, that's my 60. Where's the 60 go? Top. 60 miles, 1 hour. 60 miles per 1 hour. So look what I got. So I'm going to take 3 times 60, divide by 20. What do we get? 9. $9 per hour. So it's costing me $9 per hour to drive that car. Make sense? Okay? All right. Last one. How many miles per dollar? How many miles can I get for each dollar? Right? How far can I go down the line for each dollar? Okay, so what do I want on top? Miles, I want dollars on the bottom. So I definitely, this is the only number I got that's got dollars in it, right? So I'm going to start with that, but I'm going to put it down on the bottom. So I'm going to have $3, and that's 1 gallon. Okay, I need dollars to end up on the bottom, and the only number I got that's got dollars in it is that one, so I'm going to put it on the bottom. Okay, now what? I need gallons to cancel again, so now I need gallons down here. Now what do I got that's got gallons? I got this, right? So I need miles, so I need 20 miles, 1 gallon, right? 20 miles to the gallon. Is that going to do it? That's going to do it, isn't it? Because look what I got now. I got miles per dollar. Miles per dollar. So 20 divided by 3, okay, is what? 6 2/3, $6.67. No, that's not right. It's miles, isn't it? 6.667 miles per dollar. So I can go 6 2/3 miles for each dollar. Okay. Now again, maybe that was simple. Maybe you guys are. Maybe you could have looked at those numbers and you just could have known. Well, I just got to divide these or whatever. But I just think making your look at your units you have and making the units end up where you want them to be. So if you're trying to find angular velocity, you know you're trying to get degrees per minute, or degrees per second, or radians per second. If you're trying to find linear velocity, you know you're trying to get inches per second, or feet per minute, or miles per hour, or something. Okay. All right. So let's just look at a quick example here. So minute hand on a clock. I just thought, let's find something that moves in a circle. Okay, so the minute hand on a clock. So let's say it's moving in a smooth, and this particular clock has a 15 centimeter radius. So we're talking about the tip right here of the minute hand. So what is its angular velocity? Well, what do we need for angular velocity? What's the one formula I said you should know? That one right there. Angular velocity is just an angle divided by a time. Angle divided by a time. Linear velocity is a distance divided by a time. Really, those two. Now, yeah, S equals R theta is probably not a bad one to throw in there as well. Okay? So I need an angle divided by a time. Somebody got one? It's a minute hand, for God's sake. So we definitely know the time, right? So give me an angle and a time that it goes around. 360 degrees in 60 minutes. Isn't that right? Isn't that right? The minute hand is going to go 360 degrees in 60 minutes. Or you could have said 1 hour, right? I didn't specify what units I wanted here, but it's going to go 360 degrees in 60 minutes. You divide that out, and what do you get? 6 degrees per minute. Or if you wanted to do hours, it'd be 360 degrees per hour, right? You simply have to take a degree divided. Now, what would it be in radians? Two pi, it's going to go 2 pi radians, which is 1 full revolution in 60 minutes, right? If we're going to stay with minutes. So it's going to go 2 pi radians. We don't always put radians on when we write 2 pi, but in this case we will because we want a unit. So 2 pi, now that reduces to pi 30ths radians per minute. That would be the angular velocity of this minute hand. Notice we didn't use the 15. Why is that? It doesn't matter how long the minute hand is, right? You can have the biggest clock ever, or you can have a tiny little clock. It's still going to go around 360 degrees every 60 minutes. But now let's do linear velocity. So how much distance does this minute hand cover? So as this minute hand goes around, it's covering a certain distance, right? This minute hand is covering a certain distance. That's where we want S over T. Now let's say we're going to do centimeters per second is what we want this to be in. We want this to be in centimeters per second. Okay? So, we might have to do some converting. Okay? Now it doesn't move very fast, so maybe per second might be a bad number to use, but it doesn't matter, we can still do it. Okay, so we need a distance divided by a time. Okay? Well, how about we we go all the way around? We did that last time. We wouldn't have to go all the way around, but let's go all the way around. What distance does this cover all the way around? What distance does this cover all the way around? Come on, now you're overthinking it. We don't even need a formula that we have that we've learned right now. All you need is geometry. All you need is 8th grade. How far around that red circle is it? Isn't that just circumference of a circle? What's the circumference of a circle? 2 pi r, right? We don't even need the formula since I'm going all the way around. Now, if I was only going part way around, then there's no geometry formula for that. Then we got to use our formula. But if I'm going all the way around, how far around the circle is it? Circumference, 2 pi r. So what is it? Let's leave it in terms of pi. There you go. 30 pi. There's r. 2 pi r. 2 pi times 15. 30 pi. Okay? Now, all that is, though, guys, all that is this. Right? It's the arc length, but we're going all the way around. So what's theta if you go all the way around? 2 pi times 15. 30 pi. But see how this formula now, this is more powerful than 8th grade because now we can do just part of a circle. How far around is a half a circle? Well, now we can just take 15 times pi. Or how far is it if we just want to go a quarter of a circle? That's pi halves. So 15 times pi halves, right? So we can do that, right? Even a pi 6 or a pi thirds around the circle. We can just take that times the radius, okay? All right, so 30 pi is how far? That's 30 pi centimeters. Now, how many seconds to go all the way around? If we wanted to go right to seconds. It's 3,600. Now, maybe you didn't want to do that. Maybe you want to do what we were doing earlier. To go all the way around, it takes the minute hand 60 minutes. Unless you're in math class, and then it seems like 800 minutes. But it's 60 minutes, right? That's the look on some of your faces right now. 60 minutes, okay? All the way around in 60 minutes. But we want centimeters per second. So here's where the science thing comes in. 1 minute, 60 seconds, right? Minutes cancel. Now you got centimeters per second, right? So 30 pi divided by 3,600. 30 pi divided by 3,600. You could go to a decimal. You could just cancel a 0. That'd be 1 and 120. So it'd be pi over 120 centimeters per second. And you could get a decimal out of that if you wanted to. Okay? That's where we're going to go with this. That's some of the stuff we're going to do. But again, all we needed was an angle divided by a time or a distance divided by a time. And we got the distance by doing this right here. Okay? That right there. All right. So, I'm not going to show you this. I've added some 4 IXLs that have to do with what we're doing right now. This is converting radians to degrees, so that's good help in being able to get that. So getting those done by the end of this week would be good. It's also got some coterminal in radians. Probably has some in degrees too. Okay? The IXLs, by the way, I've started listing up there. So that's our total IXLs we have to have done. Probably, we got 2.5 weeks yet before I would say that those are all due, or that I'm going to put the grade in the grade book, okay? But it makes sense to do them this week because they have to do with what we're learning now, okay? But this is your homework for tomorrow, and it's pretty much all just radian degree conversions, what quadrant, sketch the angle, that kind of stuff. There isn't any linear angular velocity yet. We'll start digging into that a bunch tomorrow. Stop recording.